Okay, gracias. Welcome everybody to this third edition of virtual opening meeting named Sustainable Science in Organic Chemistry. Now I would like to introduce our first invited speaker, Kyle Cordova, who was proposed by Alejandro Fracaroli. Currently, Kyle Cordova is Executive Director of Research Enterprise of the journal Royal Scientific Society. Previously, he was Principal Director and Coordinator to the Berkeley Global Science Institute at the University of California. His interests are focused on the development of policies aimed to address global problems. Kyle Cordova got several awards for innovation and for initiative toward global science. He has authored more than 40 publications, including 5 in Science and Nature family journals. His research is focused on using the principles of reticular and material chemistry for application in clean energy, health, and environment. Today, Kyle Cordova will share with us his finding on the chemistry of reticular material for carbon dioxide capture, regeneration, and conversions. Welcome, Kyle. The audience is all yours.
Bueno, un minuto, Manuela, un minutito. Bueno, como ya dijimos, no va a poder asistir en forma personal, no va a poder asistir básicamente por razones personales. Vamos a entonces transmitir un video que nos ha enviado. En este caso en particular, el espacio de preguntas lo vamos a dejar a que se la hagan en forma particular a través de su email, digamos que lo vamos a publicar ahora pronto en el chat. Bueno, Manuela, gracias.
I'm sorry that I cannot be with you there virtually, in person. This morning I felt unwell. I think a moral of the story is don't eat fish or sushi in a landlocked country like the one I live in, which is Jordan. But again, I hope this recording is okay and that you enjoy my talk. My name is Kyle Cordova. I'm the Executive Director for Scientific Research and Assistant to Her Royal Highness Princess Sumaya bint Al Hassan for Scientific Affairs. Today I'm going to be talking to you about the chemistry of reticular materials for CO2 capture and regeneration and conversion. I first would like to start with thanks to an old friend and a mentor, Professor Alejandro Fracaroli, who's pictured right here. This is myself about 10 years ago in Japan. I was a graduate student at UCLA, and he was a postdoc at the National Institute of Material Science. And this is where we first met and then continued our relationship to when we were both at UC Berkeley. So it's been 10 years of great friendship and mentorship by Alejandro for me. And it's really an honor to be here presenting to his colleagues in his home country. And I hope that we have 10 years more together, Ali. So I know this is a conference on organic chemistry. I'm not an organic chemist per se. I'm a materials chemist. And so I approach a scientific project towards a materials viewpoint. And when I'm thinking of materials, there's a basic concept for designing and engineering them. And that's that chemical structures that are extended and periodic are entirely composed of joints and links. And so here you see a joint, here you see a famous drawing by the artist Escher, and you see a joint right here connected in 6 different ways by these linear joints to another, or by these linear links to another joint, and they kind of come together in this cubic form with a lot of open empty space to explore. And so the chemistry then becomes, well, how do I transform this abstract joint and this abstract link into a chemical form? And so to do that, we have 2 basic requirements. You have to define molecular building blocks that have directionality. So when you look at this cube, this joint here, it is directional in its connection through 6 different ways. It has a coordination number of 6. It has to have a well-defined coordination geometry. We know that in chemistry, anything that has directionality should have a good geometry, and we can take advantage of that. And so our first molecular building blocks, which are our joints, are well-defined directional metal clusters. Those are multinuclear metal clusters. And so here you see a square paddle wheel. This is copper acetate, the crystal structure of copper acetate that's connected in 4 different ways in the shape of sort of a square. You can have a triangular sort of cluster like this, or a trigonal prismatic like this one, or more complex octagons to this octanuclear cluster. This is octahedral with zinc acetate. And so I hope what you're getting the sense of is that chemistry, inorganic chemistry in particular, has provided us with a lot of discrete metal clusters that are well defined in their coordination geometry, and they are directional in the way that they can be linked up. You get more complicated ones like these rods or these dual rods and so on. So our second molecular building block is our links. And these also meet those 2 requirements of being well defined and directional. And these links are typically organic molecules. And so we classify them as di, tri, tetra, whatever topic, meaning that they can connect in the case of ditopic in 2 different ways. So ditopic will always be linear. Tritopic is triangular. Tetratopic, when you can connect in 4 ways, you have multiple shapes now. Now I can make a shape, a well-defined coordination geometry like or directional like a rectangle or a square or a tetrahedral. You can get starting into hexagons and octagons and dodecatopic structures. And since this is an organic sort of symposium, I thought I'd show some structures of the organic molecules that we make in order to link up those metal clusters. These are ditopics. They can be all sizes, but again, because they're ditopic, they're linear. Tritopic is you can connect 3 different ways. They're mostly triangular, but you can play around with how the triangular is sort of skewed. So here you have a longer sort of triangle, the shorter side over here, whereas here you have an equilateral triangle. And if you notice that all of the coordination geometry is based on, or all of the coordination is based on carboxylic acids, and that's because they can chelate to those metal centers that serve as the joints of the structures. For tetratopic, like I showed you before, you can have the tetrahedrals, you can have a rectangle here, you can have a square, you can have a porphyrin-based square. With hexatopic, you get even more fancy sort of linkers, and same with octatopic linkers. And so, because we know how those molecular building blocks, how to create those molecular buildings, we can start to design end structures with a specific, what we call topology. And so, since the molecular building block, the first one, the joint, is a metal, we call it a metal, and since the linker is organic, we call it an organic. So we call it, if we put it together, we call it metal organic frameworks, or MOFs for short. And so here I'm showing you just a sort of example of what we do on a day-to-day basis of designing a new MOF. If you want to take a cubic MOF, you have to define your joints and your links. Here's my joints, which are the blue balls that have directionality in 6 different ways. Each blue ball connected by a linear line, and that's my linker. If we know what sort of shape connects in 6 different ways or has a coordination number, that's usually an octahedron, so we replace that with the octahedron. You can connect octahedrons again with a linear line. Using your chemical intuition, zinc acetates structures are, it's 4 different zinc atoms coming together to form an overall octahedral shape, so I can replace that octahedral generic sort of polygon with a zinc acetate, and I can connect zinc acetates with the linear benzene dicarboxylic acid for my joint. This yellow ball means nothing in terms of chemistry, it's just more of a guide of the eye to understand how big the pores are. But here's a MOF, and so I just kind of, that's the basic design principles of making a MOF. Now today I'm not talking to you about reticular chemistry and design materials, I'm talking to you about how do we make those materials to solve a big problem. And in general, I think there's really 4 molecules that are changing the world. Hydrogen, Europe is going crazy about hydrogen right now, as potentially adopting as a fuel. It is the cleanest fuel, doesn't generate any sort of greenhouse gases. You have water in a country like my own, that I'm living in right now, where water scarcity is a major problem. And you're the 2nd poorest water countries in the world. You want to have access to fresh, cleaner water immediately. Methane is not great, but it's cleaner than petroleum, and so maybe getting to hydrogen, you have to go through natural gas and methane. But currently we have a problem with the carbon dioxide, which is being emitted in massive amounts around the world. We know it's detrimental to our planet and it's causing and accelerating climate change. And so let me show you a brief little video to give you a sense of what these MOFs look like on the atomic scale. And so what will come up to one of these nanocrystals. In this case, it's a cubic morphology. It doesn't have to be a cubic morphology. And we rotate the MOF. The gas starts to form around it. You see sort of this open free space that happens by linking together joints by linkers. The gas starts to come inside of the MOF because it's attracted to something that we've created inside those MOFs, and then it's stored. And so really our question when it comes to CO2 is how do we design internal pore environments, not only the structure, but internal pore environments that are capable of selectively capturing carbon dioxide, keeping it there, and then potentially converting it to something else. And so when we look at the CO2, the carbon problem, we know that oil is pumped out of the ground, refined, and then used in whether that's cars or in coal-fired or in gas-fired power plants, petroleum-fired power plants. But in the US alone, 17 tons of CO2 is released per capita, and that's for just driving your car. And CO2 is released in the form of exhaust, and so that's where our journey in the CO2 problem begins. We are able to create materials that selectively capture that carbon dioxide before it goes into the environment. But the question then becomes, well, what do I do with that CO2 once I capture it? And so we can make MOFs that have very high surface areas that can store that CO2 in large amounts so that you can transport it and then eventually inject it into the ground. Or you can develop sort of MOF catalysts or reticular material catalysts that can convert the CO2 to value-added products. And so today I'll take you on this process where we go from capture to conversion. I really talk about storage and transportation. I always like to give people a sense. I don't fully appreciate the CO2 problem until I kind of work it out on a piece of paper. And so this is kind of a fun little sketch. This is not petroleum based, but this is a coal-fired power plant. And say if you take a medium 500 megawatt CFFP coal-fired power plant, if you do some calculations and it's just some general chemistry, stoichiometry, you'll end up with 4 megatons of CO2 per year. I know that that's a lot in an abstract way, but I don't really appreciate it until I go a step further. And so in the case of a coal-fired power plant in Oregon in the US, it's called the Boardman Power Station. It consumes roughly 4,500 tons of coal per day. And so if you can carry 115 tons per railroad car, that's roughly 38 railroad cars per day of coal that is used in order to power Oregon State in the United States. When you burn that coal, you produce roughly 600 cubic meters per second of flue gas, and flue gas is the exhaust after burning it. So you have 4 megatons per CO2 per year for such a power station. 38 railroad cars of coal being burned per day, and generating 600 cubic meters, producing 600 cubic meters per second of flue gas. So let's put that into further perspective. If we take the lovely ex-president of the United States, Trump, and his tower, and we calculate its internal volume, it's 262 meters high, 48 meters long, and 24 meters wide, which equals to 302,000 cubic meters. The power station, the flue gas that I just talked about, would fill the Trump Tower every 500 seconds. That's every 500 seconds. That's how much flue gas it's generating. And of that, 12% is CO2. So you're producing a large amount of CO2 into the atmosphere. And that's just one coal-fired power plant. And there's thousands of them across, or tens of thousands of them across the world. And so the question then becomes, well, how do you capture that flue gas? And to capture, or how do you capture the CO2 from that flue gas? And so you have to understand what it is. And so here's the composition of air. In flue gas, you have 70 to 75% nitrogen and 11 to 15% CO2. You have other minor components like oxygen and hydrogen, which are not detrimental to the environment. And you have some detrimental things like SOx and carbon monoxide and NOx. But the main competitive gas is water vapor, or gaseous species is water vapor, when you're trying to selectively capture CO2. And that's because they compete for the same sort of sites, absorption sites. That's what I was looking for, sorry. So when you're designing something, you have to know how to capture CO2 in the presence of nitrogen and water mainly. And so when you develop CO2 adsorbents, there's 7 different criteria that you have to think about. The first is that you want to have a material that has a high absorption capacity. And what I mean by that is that if you want to capture CO2, you want to capture a lot of it. I think that makes intuitive sense. The second criteria is that you want to have high selectivity, right? You want to capture CO2 and CO2 only. You don't want to waste any of that capacity on something else. The third criteria is you want to have fast absorption kinetics. You want to be able to capture it and release it very, very quickly so that you don't, so they can continually process large volumes of flue gas. You want to be able to regenerate the material quickly so that you can reuse it. You want to make sure that material has a long-term stability. You don't want to have to change that out. Tolerance to other components like oxygen, or in some cases you have SOx or NOx, and you want to be able to produce it at a low cost so that it's economically feasible to capture the CO2. And so when you look at the gamut of materials, really you're talking about MOFs and ZIFs, which is a subclass of MOFs having some of the highest achievement when it comes to the 7 different criteria. And why is that? Well, it's because we know on the molecular level, on the atomic level, the structural features that are important for selectively capturing CO2, and there's 6 different ones. The first one is that you have a coordinatively unsaturated metal site, so you have a metal site that is missing a coordination bond, and so CO2 can come and absorb right there in a very strong fashion. The second is you have a polar group that can induce a quadrupole moment in the CO2, and that's a strong interaction. So CO2 can come and sit and absorb there. You have heteroatom linkages that are also polar, and they can induce those quadrupolar moments. You have alkylamines that allow for chemical bond formation, or in a chemisorption sort of process. You have silicon hexafluoride that's ionic and also can induce quadrupolar moments. And so you have ionic sort of structural features, and you have hydrophobic, which prevents the other materials from being present. Now, in the synthesis of tropazide ZIFs, so my first foray into CO2 capture was the synthesis of tropazide ZIFs. And ZIFs are MOFs, but they have zeolitic sort of features. And so in this case, you have a tetrahedral zinc 2+ that reacts with 2-methylimidazole, as well as a second linker that is a benzimidazole sort of derivative, and that forms ZIF 300, 301, and 302. When we made these, we proved that they're porous, so with using a nitrogen absorption isotherm at 77 Kelvin, they have a 680 square meter per gram surface area, which is a lot. We proved that they're hydrophobic due to the fact that they have those big benzyl groups in the 2-methyl group that kind of block out water. So this is a water adsorption isotherm. You see very little uptake at 25 degrees Celsius in comparison to porous carbon, like charcoal, that we know is hydrophobic. So it's very similar sort of profile. And then we start to do CO2 and nitrogen adsorption processes for each member of the series. And so this is the CO2 and this is the nitrogen. You have very low uptake for the nitrogen, and you have moderate uptake for the CO2. But what's important is the slope of the initial uptake, which gives you an indication of how strong the CO2 interacts with the framework. And so in this case, it's quite a lot, leading to moderate selectivity, CO2 nitrogen selectivities of 17 to 22. We then take this to, we want to understand it in a dynamic sort of setting. That's a in a dynamic kinetic setting. Previous were thermodynamic isotherms. And so this is called a kinetic breakthrough experiment. And what we do is we take a bed of material and we flow a gaseous mixture over top of it, 82% nitrogen, 18% CO2, and then we monitor the effluent. And so what we see that comes out is 100% nitrogen and 0% CO2 until around 180 to 250 seconds, where the CO2 then starts to break through. And what happens at this time is that the CO2 is being selectively captured by by the ZIF. So this is showing in a dynamic kinetic setting that the material performs well. That's exciting, but again, when I showed you the components of the flue gas, you need to understand water's role as well. And so here we do the same exact experiment, same exact composition of nitrogen and CO2, but this time we do it with a high relative humidity, or wet nitrogen, 98% relative humidity. The breakthrough curves are they are identical to the dry situation. So it shows you that the wet has no effect on the capture of CO2. This was really, really exciting when we first reported this. And then we looked at the uptake capacity in this dynamic breakthrough study as a function of the CO2 nitrogen selectivity, and we see that they're roughly correlated. But really what the next step was is we have to somehow increase the selectivity, which would increase the uptake capacity, but we can't lose that hydrophobicity because that's how we block out that competitive water adsorbent. And so my group here in Jordan has been collaborating with Professor Yubiao Zheng's group at Shanghai Tech University in China. And our original goal was just to make new ZIFs based on three-membered rings. And so in zeolite chemistry, three-membered ring zeolite type materials are really important from the viewpoint that they typically form they form materials that have high porosity and are not very dense. And so we thought, but the challenge with making three-membered rings is that this is sort of a strain. And so what you have to do in zeolites is you have to go away from the silicon-oxygen-silicon bond. You have to go to a germanium-oxygen-germanium bond that sort of lessens the strain of the three-membered ring. And so when we try to translate this to ZIF chemistry, we played around with the imidazole zinc imidazole bond angle by replacing one imidazole with a benzotriazole, which sort of also released the strain. And so we have a benzotriazole and a benzimidazole derivative, which allowed for the formation of this MPO type based on three-membered rings. Again, that's all very much reticular materials design, has nothing to do with CO2. But the fact that our structure that you're seeing right here, ZIF 1001, has channels lined with these benzene rings shows you that you have a hydrophobic sort of pore environment. And so we did the same thing as the chabazite ZIFs, and we measured the CO2 and the nitrogen. These materials are effectively nitrogen phobic. There's zero uptake of nitrogen. And at CO2, you can see these sort of higher uptakes with a steeper initial slope, meaning that the CO2 interacts with the framework. We performed those same kinetic breakthrough experiments, and so this is that experiment, but presented in a different way. Nitrogen effectively comes right out. There's no absorption of it, and CO2 is held within the pores of the moth for up to 12 minutes. Which shows you that you have a higher selectivity and a higher capacity in this ZIF series, and that does not change over 5 cycles. I should note that this is under high humidity, so this is nitrogen, CO2, and water separation. So we submitted this. This is unpublished data, and I hope it's in a journal near you soon. So if we revisit those structural features, we took a lot of advantage of the hydrophobicity here, but we also have played around with polar groups in materials that are similar to MOFs, called microporous organic polymers. And so if you remember back to the criteria, in low production costs in Saudi Arabia, they have a lot of means of producing polymers at scale. And so they were really interested in MOFs, but at the same time, they really wanted to look at polymers that were porous and could capture CO2. So here we take this aniline with pyrrole and paraformaldehyde. We do what's called a polycondensation, Friedel-Crafts polycondensation reaction, and you have this methylene sort of cross-linking agent that brings the pyrrole and the aniline together, and you form a porous structure. We do all of the same things I showed you for the ZIFs, and we prove that that they're capable. But in this one, we took it a step further, and we did a lot of cycling of the kinetic breakthrough experiments. And so here, up to around 9 minutes, you see that the breakthrough time, the CO2 dynamic capacity and selectivity doesn't change over at least 50 cycles. And so that was really, really exciting. And we don't think it would change even if you go higher. And just to kind of show you that we took this one step further, and applied it to not flue gas streams, but natural gas streams, which are often contaminated with the very difficult to remove hydrogen sulfide and carbon dioxide. And we ran a breakthrough experiment here with those same microporous organic polymers. We see that methane comes out immediately. CO2 is sort of trapped for about 10 minutes. And then H2S is trapped for up to an hour. And so therefore you can selectively produce pure methane while CO2 and H2S is trapped within the microporous organic polymers. We proved that this is cyclable over 5 different times after a short little regeneration process. And it really kind of shows the fidelity and the utility of these microporous organic polymers to capture CO2 with even more difficult to remove contaminants like hydrogen sulfide. So the question then becomes, if you capture the CO2, what do you do with it? And so with MOPS, we dive right into the structural features again. How do we design these things in order to be effective catalysts or heterogeneous catalysts? And so there's 4 different structural features. The first is that you have defects in the MOPS. If you are missing a linker, that can generate what is called a Lewis acid defect. And that Lewis acid defect allows the CO2 to come here and be transformed. You can have purely metal-driven catalysis, meaning you have a site-isolated metal or metal cluster that is isolated in the larger framework that allows for the catalysis to happen. You can have linker-promoted organic catalysis, so you can have organocatalysis, or you can sort of stitch on a coordination compound or a molecular catalyst that can do that conversion. And you can have a combination of both SBU and linker. And so with colleagues in Spain and in Vietnam, we designed this MOF based on this hexatopic linker with zirconium. It formed these beautiful structure with its hexagonal pores, but when you rotate the structure 90 degrees, you actually see that 2 out of the 6 carboxylic acids of the linker are actually not bound to metals. They're open, which allows for a potential site to do some cool organocatalysis on the linker. Here's a MOF structure. It's really a beautiful STP. It's called MOF 892. It has a high surface area. It has those open carboxylic acids and also has open metal sites as well upon dehydration. And so what we did is we took MOF 892 and we fed it with epoxides, propylene oxide, and various derivatives together with CO2 to produce cyclic organic carbonates and up to 96% conversion and 86% yield and 86% selectivity and 82% yield under very mild conditions. We took it a step further and went to these olefins, added an oxidant along with CO2 to produce a cyclic organic carbonate, and that still produced these same sort of numbers. And so if we looked into why it works so well, we have accessible Lewis acid sites from the metal upon dehydration. We also have those open carboxylic acid sites that work as Brønsted acid sites for catalysis. And so if you dehydrate this by just cleaning them off up a little bit, you can release water, you generate a coordinatively unsaturated metal site. Your substrate epoxide can come and interact with that metal site. You have the co-catalyst N-butyl ammonium bromide that does a backside nucleophilic attack to open up the ring. You then have this interaction that CO2 then can insert into this reaction like you see right here. There's ring closing, kicking out the bromide to regenerate the co-catalyst N-butyl ammonium bromide and to produce your product, which is a cyclic organic carbonate. That's great, but if you can't dehydrate it, then it seems that the Brønsted acid site, this right here, this open carboxylic acid site, would be where the catalysis happens. And so what we did is we did this kind of cool little technique where we post-synthetically methylated the carboxylic acids to form esters. And we did the chemical fixation of CO2. We did this catalysis again. And what we found was that the efficiency and activity of the catalyst dropped massively. And so that showed the importance of these open Brønsted acid sites. And so again, it's the same sort of mechanism. You have a hydrogen bonding between the substrate and your open carboxylic acid. Your N-butyl ammonium bromide attacks. You have CO2 insertion to close it and to form the ring. You reform your co-catalyst with the cyclic organic carbonate. And really, this is the dominant structural feature in the catalysis. My last 5 minutes, I'll kind of wrap it up here in addressing CO2 reduction catalysis in MOFs. And we wrote a nice paper in 2018 in Nature Materials, kind of addressing the question of, is reticular chemistry the answer for the next generation of CO2 reduction catalysts? And I hope to convince you. In CO2 reduction catalysis, there's 3 different sort of components that you have to think of. Selectivity, which is based on chemical features. Nature is very good at this in terms of photosynthesis, and molecular catalysts are very good at this in designing and making sure that you can have the proper electron transfer and all of those things that are needed for selective reduction. Activity is where you have your structural feature. If you have a large surface area, you have a lot of different active sites. Nature is also very good at this, and so is inorganic catalysis, like metals and metal oxides. Efficiency is where you can tune your optoelectronic properties in order to do photo or electroreduction catalysis. Molecular and inorganic, your synthetic catalysts are very good at this, but nature is not. It might seem counterintuitive, but honestly, if you think about it, a plant only takes 1 or 2 different CO2 molecules at any one time and can't process the large volume that is present in the air. And so reticular chemistry and MOF sort of embody all of these different catalytic platforms into one. We can tune the chemical features to be selective. We have the structural features that allow for high activity, and we can tune the optoelectronic properties in order to improve efficiency. And so in terms of photoreduction, we've had 3 different generations of the development of MOF photoreduction catalysts. The first generation was focused on the selectivity and activity components. You would site isolate a metal cluster or a coordination compound on your linker in order to do that sort of catalysis. You play with the activity by increasing the surface area and tuning the pore metrics. And you played also with the selectivity by creating MOFs with coordinated and saturated metal centers. The second generation focused on photonic efficiency, where you played around with the electronic character of the organic linker, and you engineered the band gap by functionalization or by extending the pi system. You also did things like play around with plasmonic silver nanocubes in order to enhance that effect, where you can intensify near-surface electric fields in order to be more photonically efficient. The third generation was the electronic efficiency, where you added things like photosensitizers that would enhance the quantum yield. You doped the metal clusters with in order to modify the electronic character of those clusters. So in this case, it's zirconium with titanium. And you really try to focus on improving the electronic efficiency of your photoreduction catalysts. Now, there's really some great work being done at MIT with Dinka's group and others. You're focusing on improving the orbital overlap between the metal and the linker. So that means things like creating metal thiolate bonds or metal amidate or metal semiquinone bonds. And if you kind of put those all together, really the consummate solution is that you have a single crystal, ideally wrapped around a plasmonic nanoparticle that can help with the electronic efficiency. You have a metal cluster that has efficient electron transfer to CO2, so you're looking at things like iron, cobalt, or copper. You have a photosensitizer either stitched to the framework or floating within the pores that enhances quantum yield. You have those metal clusters that have a high density of open sites so that you can have a high selectivity. And you have a linker metal bond that allows for efficient charge transport. And really the goal is to get, to put that all together with a photoelectrochemical process. There's some really great work on electrocatalysts like COFs, another type of reticular material covalent organic formate, where they're able to reduce CO2 to carbon monoxide or formate or methane. And if we can put that together with the sunlight so that you have some sort of photovoltaic cell, then that's really kind of the end game. So here I want to stop and I want to acknowledge the scholars behind the success. I really am thankful to my colleagues at UC Berkeley, where I was for the better part of the past decade. Professor Omar Yagi, Dr. Hiroyasu Furukawa, some great crystallographers, and Dr. Felipe and Christopher Trickett, and a lot of the CO2 reduction work at the end was with Christian Dirks. In Vietnam, who did the ZIFs and MOF 892 catalysts, Professor Nguyen, Professor Fung, and Dr. Hong. This is our team in 2015. There's Omar and Hiro and myself. And then the microporous organic polymer work was done in Saudi Arabia. Here was our team in 2018 with Professor Zain, Dr. Bassam, Dr. Asif, Dr. Mahmoud, and Professor Offman. I have to also thank my current team that was working on the 3-membered ring ZIFs that we're currently trying to publish. This is a materials discovery research unit. I have to thank them for the resilience. We started, building the lab here about 6 months before COVID hit. So all of them have been very strong in making sure that they're progressing in their science while dealing with this public health thing. You might have noticed that I have a unique title, and then I'm an assistant to a princess, and this is the princess who serves as the president of our organization, the Royal Scientific Society, Princess Sumaya bint Al Hassan. I want to thank her for her immense support for not only, our research group, but for science in Jordan and region, and championing science as a tool for peace in a region that doesn't know a lot of peace oftentimes. This is her father, who is a very, very important global figure, and he visited last week, and so we had this nice little occasion together. I'd like to thank the funding from Jordan, from the Shoman Foundation and the Ministry of Higher Education and Scientific Research, funding from China and from the UK, as well as Saudi Aramco. And again, I apologize for not being there with you in real time. Like I said, I hope this recording was okay. I'm happy to answer any emails that you have. You can just simply email me, kyle.cordova, my name, at rss.jo. I'm really, really happy to answer anything. And again, I wish you guys a successful online meeting. Take care. Thank you very much.
So we want to say thank you to Kyle, especially because he has to record it very quick and very early this morning, his presentation. Was a great presentation.